Now we look at any function from the natural numbers to the power set of the natural numbers. And here I've written each element of the range using its infinite bit string representation. So keep in mind that that means that each of these is either a 0 or a 1, right? Each of these, we just circle some at random. Each of these is either a 0 or a 1. And again, this is the range, right? In the yellow is the range, right? Why is that the range? Because the range is all the outputs, and these are all of the inputs, all of the natural numbers. And so using the absent bit string rule, we would go along here and say, okay, is that a 0 or a 1? Remember that capital BI equals 0 if BII equals 1, and 1 if BII equals 0. So if that's a 0, then that's a 1. If that's a 1, then that's a 0. And then this cannot equal B. Moving to that one, if that's a 0, then that's a 1. If that's a 1, then that's a 0. So they can't equal there as well. And similarly, on and on and on, down the diagonals, down the diagonal. So we find that there's a D and E there, and so then F is not onto. Now you could consider this a proof if you want. I didn't write everything out, but I explained every piece of the proof. So now we can take it as fact that any function from the natural numbers to the power set of the natural numbers is not onto. So I guess I should say, if f is any function from the natural numbers to the power set, then f is not onto. Okay, I proved that statement. So just to reiterate, I proved the statement that if f is any function from the natural numbers to the power set of the natural numbers, then f is not onto. And the reason why this is because, excuse me, there's just way too many subsets of the natural numbers. The infinity of the power set of the natural numbers is much larger, much, much, much larger than the infinity of the natural numbers.